So, I have a few things to say. So, I was going to go over a little bit about what he did last class. So, I'll just say really quick the thing about quantum dots is the thing that we've done last office hours where you have a box with three widths. So, I guess they're called quantum dots. And if you have, let's say it's a cube, so the lengths are all L, then he showed that based on the energy formula we had last time, we have zero, which is not a state you can have, but this is energy is zero. This is energy, and then the lowest energy, the ground state. Remember, it was like n x squared plus ny squared plus nz squared times what is it, h bar squared pi squared over 2ma squared, maybe? 2ml squared, maybe. Yeah. Yeah, and so the lowest state is the ground state is 3 times, well, I'll just call this all like, what should I call it? I don't know, EG for like, well, it doesn't mean ground, but H, big H. I'm just naming this big H. No one uses this for anything.
You said that was the ground state?
The ground state is 3 times this H.
Okay.
I just don't want to keep writing
Thank
this.
you. Yes, that's fine.
You should not remember that this is called H, because it's never called H. But I just don't want to keep writing it. And the point is that this is the state that corresponds to 1, 1, 1 in the convention that this is nx is ny and nz. And so you just compute this, you square them all. And then for the next state, this is the first excited state, there's 3 actual different states, and this ends up being 6H, has energy 6H, this is the energy level. And we know that, first of all, we know there's 3, we know it's 6 because that's the 2, 1, 1 state, right? And so this is 4, 5, 6, okay, times this. And we know there's 3 because the 2 could be in any of these places. Then we can have another state which has value 9H. Also 3 of them where we basically pick where 2 of them are 2 and 1 of them is 1. So we have 3 choices of where to put the 1, which is these 3, and if we compute that, that's 2 squared, which is 4, plus 2 squared, which is 8 total, plus 1, which is 9.
Got it.
And we can rearrange these in any way. The reason they're all the same energy, as just to repeat all this stuff, the reason they're all the same energy is because if we switch the values of nx and ny, put the 1 here instead, this number is the same. But it's a different state because that means that a different quantum number has a different value. So the states are determined by 3 quantum numbers. Every line you draw here that represents a state has to have a different set of quantum numbers. So this is called the state. This is the energy. States that have the same energy are degenerate states, and that's why you get these multiple lines. The next one you get is 11. 11 is from 3, 1, 1, I guess. So 11H, which is from 3, 1, 1. But there's 3 of those because the 3 can go anywhere, right? And how do you get 11? It's just 3 squared, which is 9, plus 10 plus 1 plus 1, which is 11. And then then you get a 12. So they're not going sort of evenly at all. Right? And the reason is because why would they don't have to go evenly. Like, it's not like if we had one quantum number, like if we just had a one-dimensional one where cover this up and you just get n squared times something, they would go up kind of in a nice way because every time you increase this, you're just like, it would be like 1 and then 4 and then 9 and then 16 and then, like, it would go up in a nice pattern. Yeah. But because we have 3 and we can increase any of them, I mean, there is a mathematical relationship, of course, it's just very complicated. It's not something you could just read off. This state, by the way, is the 2, 2, 2 state, and there's only one of them because, of course, you can't rearrange them, it's the same state.
Got it.
So there's only one state. Anyway, we keep going, and as I think I mentioned last time, it's just an interesting mathematical fact that there are states with 6 possible, which is the 1, 2, 3, because you could, anyway. That's not, you'll never have to, I'm sure he'll never give you a problem with like that many.
Yeah.
Because 1, 2, 3 would be like 9 plus 4 plus 1, which is like 14 or something. So So I guess, well, 14's, anyway, whatever, it doesn't matter. The point is that that we don't have to worry too much about more than basically this. And you don't have to, again, you don't have to memorize these energy levels at all. You should not memorize them. You should just think about the actual states and then realize when you can switch things around. So the only ones that have one state only are the ones where they're all the same. And then these ones have mixtures of, actually these two have mixtures of 1s and 2s. This one is actually 3, 1, 1.
So if you're doing the energy levels 1s, 2p, 2d, 3s.
Are you talking about the SPDF?
Yeah, am I getting this confused?
Yes, I'll get to that in a second. So this is the V equals this.
Okay.
Right? V equals 0 in a cube. That's literally what this is corresponding to. If it's not a cube, if it's a like one length is different, as we saw in the last office hours, then the symmetry is kind of broken, and you get like there's not a degeneracy, because if you have like a different length under each of these three, like I factored out the L squared on the bottom here, but if we had a different length under each of them, so we had like a cube with different lengths, then switching this and this would not imply the same energy, because they're being divided by different lengths. So you don't get anything super interesting in that case. You just get a bunch of separate energy levels with one state each. The reason we have degeneracies is because they're all the same length, and so putting a 2 and a 1 versus a 1 and 2 is the same energy. Whereas if they were different lengths, you would not get that. Anyway, so this is V equals 0 inside a cube and V equals infinity outside a cube. That's a very specific, it's called the three-dimensional infinite square well. Square because it's like inside a right angle type, like there's right angles here, right? Even though it's a cube, they just call it a square. So now I'm going to erase this, and then the second thing he talked about, so these are called, I guess they're called quantum dots also, but I don't know what that means, so let's just pretend that they're called states of the infinite square well in 3 dimensions. And there's another one which is also in 3 dimensions. That's why there's no marker that erases and writes well. But if you have V equals 1 over R, now like the, that's it. V equals 1 over R, or maybe it's a minus 1 over R, it doesn't really matter. The point is that this is also very important. Well, actually, this is probably more important than the other potential, because this is like an atom. Actually, I should really write minus 1 over R, but it doesn't really matter. The minus only matters when you plug it into the Schrodinger equation, and because we call energies of electrons in atoms negative when they're bound, that's the only thing this affects. And we call the energy all the way at the top when they're ionized 0. But you could shift the whole thing, it won't really matter. I'll get to that at the end if that matters, but they usually write it like this. I just don't want you to be nervous if you see a negative. It's the same thing. But what this is if I draw it, it looks like this, and this is just an atom. So here's the nucleus. And then here's some states you could have, and we know that there's going to be states. And to actually find the states, to actually get to this, you don't necessarily know that there's these states or where they are. But to find them, you have to literally solve the Schrodinger equation again, just like we did to get the states of the box. Except the Schrodinger equation in spherical coordinates it's on one of his slides. It doesn't matter. It's incredibly complicated, as I said, because you have to use spherical coordinates. It's really complicated. The point is that instead of nx, ny, and z quantum numbers, you actually get n, l, and m quantum numbers. Oh, sorry. Let me just go back to the square thing for a second, because I forgot to say one thing, which is that, so this is E1, this is 1, 1, 1. So this is in the square well again. If you want to say how many, let's say if they said you have 12 electrons, where in the lowest energy state, where can they go? Each state can hold 2 electrons, and they usually write them as spin up and down. So I mentioned this last time. I just want to make sure, because we're going to put electrons definitely around a nucleus, obviously. So if we had 12 electrons, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and that would be it. And it doesn't matter, of course, which ones in here we put them in, right? You just fill them from the bottom. And then, and I'll just preview this is going to come back in after I finish talking about this. The level, so remember when I drew this, there was more states. It was like this, right? This was like 11, this was 12, this was 9, this was 6, this was 3.
Yep.
right? So these were the states. Now let's say I said I have 12 electrons at the ground state. The ground state, remember, this is called the ground state, but the ground state of this whole system would be you have to like pack them in. So this is the ground. This is like the lowest energy state of the electrons. This level right here, it's basically like you filled up the pool with electrons. What's this level here? And I would just call it, I mean, I guess it's just called 9 times, H or whatever, right? I mean, I drew it in the middle, but it's really just the highest energy. This is called the Fermi energy. So we're going to come back to this. This will come back later. But I want to connect it because the thing he talks about next with the bands and the Fermi energy and the Fermi stuff is not disconnected from this stuff. It's the same idea. So when we go, this is another problem I have, I think, with this, with how, I guess the problem is just with how fast we're going because you don't notice that they're kind of the same thing. But Fermi energy is the energy of like the top electron when filled. When filled, I just mean like you start at the lowest and you start filling them up. So if someone tells you, I have a square well with 12 electrons in it, what's the Fermi energy? You would say, well, I start filling them in until I get to 12, and what's the energy of the highest electron? It's 9 times h bar squared pi squared over 2ml squared. Okay. So this is called the Fermi energy. And anyway, we'll see. We'll come back to that because this is very important for things like conductors and solids and stuff like that. They don't, anyway, so we'll see. This, though, so these are the quantum numbers nx, ny, and z for the square well. For the nucleus, for the atomic nucleus, which is this potential, we get these quantum numbers. L and m are things to do with the angular distribution, which don't worry about that. That's not, that doesn't affect the energy at all. It just turns out that the energy is this number over n squared, where n is the first quantum number here. N is not the same n as here, of course, because it's a different system. But and therefore, because of what L and M are, and on the slide, you should look, if you haven't seen it in a while, like you probably have seen it in chemistry, but the L and M are coming from things called spherical harmonics. Sorry, I said you should look something up, and then I wrote this. I don't mean you should look this up. You can if you really want to. But what it is part of the Schrodinger equation when we solve the Laplacian in spherical coordinates. The theta directions, like the sort of latitude and longitude directions, are only solved by special functions called spherical harmonics, and they give us this L and M. The radial direction, as in how far away and what shell do you have to be in, are only solved by n, and therefore the energy only depends on n because the potential only depended on the distance. That's why L and M seem to come kind of something from a different place. It's because they kind of are. They're coming from the fact that you have to wrap them around a sphere, around the nucleus. The n is the really important one for energy because that tells you about the distance, and the distance is the thing that costs you energy, right? Being farther away takes more energy than being closer because of this. If this had like a sine theta or something in it, this would be all messed up and you'd have L's and M's in here. It would be a nightmare. Not that this isn't a nightmare already. But anyway, it's solved, so here it is. Anyway, and the point, well, okay, that's fine. So, and the ground state is, of course, the lowest energy state is when n equals 1, which is therefore the energy of the electron is negative 13.6 electron volts. Okay. Where we call an electron that has no kinetic energy and is not bound to the nucleus, we call that zero energy. Okay. So anything negative means it's in a nucleus somewhere, and 13.6 is like, so the difference between here and, so this is E equals 0, and this is E equals negative 13.6. This means that this is n equals 1, n equals 2, n equals 3, and then there's like, of course there's infinitely many, because, right, but then as you get to a free electron, so it's called the ionization energy of hydrogen, is negative 13.6 electron volts. If for different elements, I'm sure it's different. I don't really know much about it, but anyway, and then so what I was going to say, what you should look up is, or at least just look through, is on the page, on the slides, and I'm sure it's in the book somewhere, where it lists the possible states So just like we listed the states here, you could also list the states with N, L, and M, where if N was 1, L could only be 0, and M could only be 0. And this is called the 1s state. And if N is 2, L could be 0 or, L could be 0 and M could be 0, and that's called the 2s. If N is 2, L could also be 1. And then M could be plus or minus 1. And then this is called the 2p state, and etc. And there's like solutions you get about like L can go from 0 to N minus 1, and M can be plus or minus L or all integers in between. Anyway, it's obviously, if you really needed to learn this, it would take a while, but I don't believe in this class you need to like really memorize any of this.
Okay.
It's just, if you've taken chemistry, you've definitely seen these, and these are the actual the quantum numbers that come out of the Schrodinger equation that give you the same things. And that's why like there's like 3s and 3p and 3d and stuff, and like that's why there's no like 1p or 1d, right? It's 1s and 2s, 2p, and then 3s, 3p, 3d. Why do you get an extra letter each time you go up? That's because L can go up to, L is 0 up to n minus 1. So if n is 1, then 0 is the only answer. If n is 2, it can be 0 or 1. If n is 3, it can be 0, 1, or 2. So this comes out of the spherical harmonic. It's a bunch of obviously subtle math things. And m is like minus L all the way to plus L. That's the range of m. Sorry, it's messy looking. But basically m could be plus or minus any of the, could be minus L plus 1, to 0, plus L. And those represent just like more subtle versions of the, And in each of these are states. So these are the states. And just like in this, 2 electrons can fit in each state. 2 electrons can fit in each state, but of course, a state is defined by NLM. So so the first state is written like this, where this is now NLM. There's 2 electrons here. How many are in this state? That's 2, 0, 0. That's 2 electrons. How many fit in this state? That's 6, because 2, so the states are 2, 1, 1,
Yep.
2, 1, 0, and 2, 1, minus 1. So each of these has 2 electrons. So in the second shell, how many in total? 2, 4, 6, 8.
Can you explain the minus one? How do you
So M can go from minus what the L value is all the way up to the L value.
Oh, it's a rule. Okay.
It's a rule. Yeah, it's a rule from this.
Oh, okay.
So so that's why in the second shell there's 8. So if you like, that's the whole thing about the periodic table. In the first one, there's hydrogen and helium. That's 2 because this is just filling up that 1s shell. In the second one, there's they arrange it in a weird shape, but there's 2 here and there's 6 here, and because there's 8 in the second, 2, 4, 6, 8.
Yep.
The ones on the left are just these 2 filling up because they filled up in order, right? Then it's a little complicated because this isn't actually the order of energies. Just like with this, it's not obvious based on these numbers which order the energy is going to go in. Like this one was actually 3, 1, 1, and 1, 3, 1, and 1, 1, 3, right?
Got it.
But this one was 2, 2, 2. Like you can't tell from the numbers which go. You have to actually compute it.
Could you have a 2, 2 minus 2?
No, here negative numbers don't. Well, because remember, they appear like this. They're squared,
Squared.
so
Anyway.
they can't be. Yeah.
Never mind.
I mean, you could say there's a minus 1, but then that's just like squares to be the same energy.
Yes. Okay.
Okay, there's a more subtle reason why you can't have a minus, but we won't get into it. But it's
Okay.
it's from the.
Don't do it if you have 3 identical. Right. So you have a 1, 1, 1. You have a 2, 2, 2. Don't.
Yeah. Don't. These are the reason we know that like these numbers are positive, these numbers are positive, and these are not always positive is details from the calculation.
Okay.
We don't know that by. That's an incredibly good question.
Okay.
And to answer it, I would need to go through the whole thing, which A, would take a long time, and B, I don't actually know how to do
Okay.
because it's very difficult. But if you look up spherical harmonics, there's conditions on L and M that will literally if you boil it down to the basics, it'll tell you these statements here.
Take your
And these will be functions that look weird on, they probably have animations. It's actually kind of cool, but anyway. So, but for these, it has to be positive because of just the way we figured it out is by where we got sine functions over the infinite well, and they had to be 0 at the endpoints, and we got an integer there. And that integer we just showed, we just showed that integer, if we'd only count the positive ones, we have all the states.
Okay.
Essentially, I'll say it. Essentially, it's because sine of minus a number is the same as minus sine of the number. So the n's here actually are going in the sign to give us 0.
Yep.
And like an integer, and if you put in a minus thing, it still gives you 0 because it's just minus sine equals 0. So we only need to count the positive ones because the negative ones are identical conditions. Anyway, sorry, that's a whole divergent. But these, you're absolutely right that why wouldn't you have a minus anywhere else? It's just here. It's just a crazy little thing from here. But if you follow these rules and you count, you'll literally get the number of things in each element of the periodic table. Yeah, I mean, okay. I'm just realizing I don't quite know how the periodic table works because I know there's another one with the same number. Anyway, whatever. And then this one has like a bunch, and this is whatever's in the 3 level, I guess, which is like a bunch more. Anyway, there's more details that you could feel free to look up and tell me about because I don't actually remember. But in fact, that's how at least the first 2 levels of the periodic table work.
Okay.
Is the same way as this. We're just filling them up. And I mean, the reason here that we're filling them up is because we're going to elements with more protons. That's what defines the element, right? Mm-hmm. And if it has more protons, it wants more electrons, obviously. That's why we're stacking it. I mean, theoretically, you could take hydrogen and just give it more electrons and just don't change just keep it hydrogen, but just make it way, way more negative. Mm-hmm. And it would still make the same structure here. Right. It would still have the same shells. Anyway, so it's just that's kind of hard to do, to shove a bunch of electrons into a hydrogen. Okay, so now I'll erase all this and talk about, I'll completely shift topics to chapter 11.
Okay.
And anyway, he has a bunch of stuff about the configuration. You could go through it yourself. It's not going to be important. It might come up on something that you should read, but it's not going to be helpful if I just tell you. Because I don't really know anything more about it. So now we're talking about, chapter 11 is talking about periodic potentials. So both potentials we've just done in 3 dimensions and the ones we've done in 2 dimensions have been like squares and 1 over r and stuff. They've been like we did the finite square barrier with the tunneling, and then we did the finite square hole, and then we did the infinite square hole. That's fine, and we've done a bunch of examples. But what if you have a potential, like in real life, what you'll have is like let's say an actual material. So let's say this is like some kind of material. What are materials made of on the surface, let's say, like a metal, for example. On the surface of a metal, it's really just a bunch of nuclei of atoms, right? It's like a bunch of like iron atoms or whatever. And each iron atom has a potential like that, right? It's just a 1 over r because of the electric attraction. So you get something like this on for a while. And the electrons, and we know on metals, we don't know why yet, but on metals, the electrons are they're not like belonging to each thing separately. They're kind of shared and they kind of flow across things. And so really the electrons are experiencing this kind of potential. It's periodic, meaning that there's a distance here called a, let's say, and it repeats. So v of x is equal to v of x plus a. So now our potentials are of this form. So this just means it's periodic with a period a in space. So we're not going to actually solve it for this because this is kind of hard, but we can solve it for just like a simple, actually we're not going to solve it for anything. We're going to sort of do it abstractly because that's what he does in the notes and the book. And I don't even know if this is possible to solve it this way. But anyway, let's just say we have some kind of he uses this kind of shape to draw it just as a demonstration. So let's say the distance here to here is given by a. So this is v of x, and a is the period of an oscillation.
Mm-hmm.
So it just means that you're in a potential where it goes like this. Now the wave function, instead of the wave function being like, now the wave function is actually going to be kind of spread out over all of the electron wave function is going to be spread out over the whole surface.
Okay.
So that seems, okay, now it seems like it's impossible, but there's this thing called Bloch's theorem. It's spelled like this because he's German, but it is not pronounced Bloch, which I kind of thought it was for a while, but it's called Bloch's theorem. And it just says that when you have a periodic potential and an electron on it, the wave function looks like this. Where, I'll write it and then I'll explain it in a second. Okay, equals u, I'm running right k here, doesn't matter, is u x plus a. So Bloch's theorem is, it's not, of course, I have to tell you a little bit about what these mean, but Bloch's theorem just says that if you have a potential, an electron in a periodic potential with a period A, so that's this, or any shape, doesn't have to be, or it could be that shape, the wave function of an electron in that space looks like this. It has two terms. This U is periodic with a period exactly the same as A, so it has a periodic part, and then it could also have this extra part called a phase. You know it's a phase because there's an I, it's e to the I something, so it's like, and this is like a plane wave, like it's the solution of Schrodinger equation in a vacuum that we've seen a few times, so it's like, you know, when you're doing scatter, or when you're doing tunneling, when you solve the Schrodinger equation with no potential, you get like a plane wave, just like a sine cosine thing. So this is the solution of the wave function, but that means that there's different wave functions. So this you're not free to change at all. You can't change this u because u is just some periodic function. It doesn't matter what it is. It depends, of course, on the shape of the potential, all that stuff. But this means that there are many wave functions. For a given potential, there are many solutions for each value of k. Because k is this number here, and this you could just pick whatever you want, because as Bloch's theorem says, it should still be a solution. So, all right. I'm glad I wrote this down. So, now let's just say like, let's draw something, and this is a bunch of the diagrams in this section. Okay, a bunch of the diagrams in this section are about a thing called the sorry, that's not how you spell it. Brillouin zone, it's called. Okay, it doesn't really. Don't worry too much about why it's called this. You could look if you want to look it up. That's what it's called. But it's a plot of the energy versus the k value. Now this is an incredibly weird thing to do, because why are we plotting something over k? K is just some number here. It's not like x. But the point is that if I know what my potential looks like, and I have a bunch of wave functions, and each wave function is only different. I mean, I know how the u looks. So why don't I just write all my wave functions I want to write in terms of what their value of k is here? So, yeah. And I also know that because, let's look at this e to the I k x piece again. If I take k goes to k plus 2 pi, for example, this goes to e to the I k plus 2 pi is e to the I k times e to the I. So like the I 2 pi x, right? And all I did was just replace k with k plus 2 pi here. But this is e to the I 2 pi x. Sorry. Yeah. Wait. No, that's fine. And e to the I 2 pi is, if I write it as what am I doing wrong? Oh, sorry. I meant to do something else. I meant to say if you change psi k of x to psi of k x plus a, so all I'm doing is shifting this over, then I get e to the I k x plus a times uk x plus a, right? That's obviously I'm just literally plugging in for this. And then I get e to the I k x times e to the I k a times, now I know that there doesn't matter if the k is there, u of x plus a is equal to u of x. So I can just write this with u of x. And then I get that this is literally just equal to e to the I k a times this part, which is literally just psi of x, right? This and this together is literally just psi of x. It's this. Yeah. And now this is just e to the I times just a number. And this is just a phase. Phase means that it just means that when we calculate anything like real about this, like when we square it to find the probability of anything, this is going to go away, because when you take the probability like this, it's actually equal to psi times this complex conjugate of psi, and the complex conjugate of this has a minus, and it just goes away. Don't worry. The point is that if you have e to the I times some regular just number, not like a function, but with just a regular number, it doesn't affect the wave function at all. So the whole point of this is just to prove this is true. If you already believe this, it doesn't really matter too much. Okay.
That's actually consider a lattice separation between lattice sites. What is the wavelength of the electron block state at k equals 0? What is the wavelength of state at k equals pi over a? Depending on which band the electron is in. So obviously I gotta read this, but
yeah.
It's just the first one was talking about block states. That's why.
Yes. Well, okay, so let's talk about, they say wavelength, right, in that question?
What is the wavelength of the electron block?
So that's a good, okay. So now I want to talk, so wavelength, so what this is a periodic thing times a plane wave. It is a plane wave, and k is the same k that we've seen before with like plane waves.
Okay.
So this is very important for this factor. That a plane wave is defined by its wave number, they call it k, or wave vector, sometimes they call it k, which is the same one we used with like interacting waves and refraction and stuff last semester. But this is always true. The wavelength you could just relate to this like that.
Okay.
So if k is 0 for a given, so if they give you something where k is 0, that actually means that this is just 1, and you just get this periodic thing here, and you get that the wavelength of the plane wave is not defined. It's actually infinity. So if you plug in 0 here, you get infinity. And in the second part, they ask you about if you plug in x equals something else, you get a different.
Pi over d. Pi over A.
Pi over A, right? And A is the length of the it's how big this period is. So if you have that,
okay, yeah, it gives you that as a 0.5 nanometer.
yeah. So that is literally just plugging in here.
Does it depend on which band the electron is in?
No, so that's what I was going to talk about. So bands are, you might have like this is your potential, and so your wave functions. We know it's some plane wave times this periodic thing. So I'm just going to draw it as like this. Let's just pretend it looks like that. And this is the energy. This might be one solution, and then the next solution. Remember, like just like we saw with the box, like if I pick, there was like 3 times h bar squared pi squared blah, blah, and there was 6, but there's no 5. Like if I say when is the energy at 5, you'd be like there's no states with that energy. So it's the same exact thing. With here, you could have something like this, where there's 2 solutions, but between here, this is called a gap. There is no possible way you can get an electron. It's just like with an atom. You can have the n equals 1 shell and the n equals 2 shell. There's no 1.5 shell. If you want to put an electron at that radius, it wouldn't go there. It doesn't, it can only have this much energy or this much energy or anything with some value of n. That's the same thing with this. It's the same exact thing. It looks completely different, but it's the same idea, is that the wave functions each have some energy solution to them. They solve Schrödinger's equation with some energy. And there could be a gap here, and that's it. So what did the thing ask about?
Does the answer depend on which band the electron
Oh,
is in?
the point is that the bands all satisfy this. The bands are all still periodic. So the bands all have the same, they go, if you add A to them, they go back to the original, like they're periodic. So the bands have nothing to do with the wavelength of because that's a different part. It's like the bands have this period and it doesn't have to do with the bands. This is like a picture in the book, I think. So this is like band 1. And so now I'm gonna shift from, this is x here, right? This the x direction, I guess, the x-axis is x, and I'm drawing it as a period. But like I said, each state, each wave function is actually, I already know it's periodic like here. Each one is defined by this k, this wave vector called k. And I know that if I add 2 pi to k, I get something like 1 here, like this is also periodic. Mm-hmm. It's like a plane wave. If you add 2 pi in the exponential, you'll get back to the original. So all I need to do is define k. So I can, this is like all of the possible states I could have. So the one they just said, what if k is 0? That's this state here. It's a wave function where this k is 0, and it's already in, like, we're not talking about u anymore because u is sort of fixed. U is always periodic with period A, and it maybe has some shape or whatever. But now we're saying the different states you could have, how many different states you could have, where could the electrons be? It's not as clear as before, because you'd think, before it was like I have to choose my quantum numbers n. But now it seems like I could choose any real number for k. Like I could put k to be, it has to be between here and here because it like loops around. But if I choose k equals pi over 2a or whatever, which is here, like, yeah, that's a state too. So it seems like now we don't have any more quantum things. We have the separation of energies, which is fine. But it seems like because any value of k would still solve this, as we just saw that the thing I just erased was showing that every value of k solves this, it seems like now there's infinitely many places I could put my electrons. I would just have to pick a value of k, plug it in, and then it would give me a wave function that would be in this system. So now this is where we get to question 2. I'm segueing nicely into question 2, which is I actually forgot what question 2 says.
Verify that delta x, delta px, delta y, equals h cubed corresponding
Yeah.
to one electron state gives a volume of 2 pi cubed of K
Right.
space for one electron.
So what it's trying to say is that you can't fit them super close together because
Yeah, by them you mean the electrons.
the electrons, yeah. So each dot is 2 electrons because each dot is a state.
Got it.
So let me write this somewhere. Each dot is a state which equals 2 electrons. So I don't know if it really. They might ask you something about. I don't know if they will, but just keep in mind that I'm drawing states here, and each state can have 2 electrons because they can have spin up or spin down. Oh, okay. So sorry. So the thing is that basically by the uncertainty principle, the fact that if a state can have a certain momentum uncertainty and it can have a certain position uncertainty, and the product of those is, and you can look it up, it's, what is it, h bar, something, there might be a 2 somewhere, whatever, it doesn't matter. The point is that each state can't actually you can't pack them infinitely close together because of the uncertainty principle. So what you need to do is just say that each one takes up this much space. So if I put them here and here, the separation between these two is going to be delta kx, which is equal to, by the uncertainty principle and something else. Yeah, by the uncertainty principle, it's this where delta x here is going to be the total range of space that. Actually, hold on. Let me think about that for a second. Uh-huh. Yeah, so I think that delta x is going to be the total space that we have allotted for each. Okay. I'm a little confused because in the slides, they write delta k equals 2 pi, which means that delta x equals 1, which I don't see why that's true. So I'm a little suspicious of that. I believe that it's just this. Delta x is the total range we could have. And so therefore, yeah, I mean, that sort of makes sense because then if we had a smaller range, if the crystal, this is called a crystal usually, by the way, this is a one-dimensional crystal. You could have three-dimensional, and there's a whole field of study about crystals in 3 dimensions, which is just unbelievably boring. I don't know why anyone does it, but you could do it, and people do. Actually, most people in physics in my building do that. Not with crystals, but with stuff like. Anyway, the point is that I'm trying to think if this makes sense. If you have a bigger distance between your crystals, if you have a bigger delta x, you would have a smaller delta k, and therefore you could fit more. So that kind of makes sense, right? You could sort of fit more. You could fit more states. Sure, why not? Okay, I'll come back to this. I believe this is.
Why
This
does
is
fitting
fine.
more states
So-
beneficial?
Well, it's not
Here.
necessarily, but it's just if you want more electrons here.
Okay.
I just mean like how many electrons can you fit? Obviously, you want to pack them closer together if you just want more. I mean, you don't. I don't know. You don't have to want that.
Okay.
But if one wanted to pack more electrons in, what would you want about your crystal? Would you want it to be very narrow or not? Yeah, it's just bothering me because yeah, I mean the question okay, let me erase this. And let's just actually do the question because the question doesn't ask you about an actual thing.
Okay.
But the question, I believe, we could start with this fact, which is the uncertainty principle. This is just true of quantum mechanical systems. It has nothing to do with crystals specifically or electron wave functions or anything like that. Therefore, delta x, delta px times delta y, delta py times delta z, delta pz, which is what the thing asks, is h cubed. Okay. And then delta p is actually just this is called the momentum. Delta p is called the momentum, but there's another thing called the crystal momentum, which is h bar delta kx. So delta k is this delta k up here. So it's sort of the one we really consider in these periodic things. Delta p is the actual uncertainty in the momentum for like a free state, and they're just related through h bar. It doesn't really matter. Therefore, all three of these p's we can replace with h bar delta k of that variable, and therefore we have, and I'll write it all at once, delta, and I'll collect all the coordinates times delta kx, delta ky, delta kz, right? Times, but now we have h bar here and h bar from here and h bar from here. So this is actually times h bar cubed, right? So I'm just starting from uncertainty principle cubed,
Yep.
right? That's all I did. So I'm not actually using anything that's given in the problem yet. I'm literally just trying to go from the uncertainty principle, cube it, change coordinates from p to k, because the uncertainty principle is stated in terms of p, but I really want the momentum, the sort of crystal momentum, as it's called, k. And this, so therefore I get this, it's times h bar cubed. It's h bar because that's just the definition of k. So the definition of k, so I'll write it as p equals h bar k. This is also again, it's just a redefinition of things. And this is equal to wait, so we want to show that this sorry. Yes, so that this is equal to h cubed, right? Because that was just this. It's just this is all equal, right? So those are equal. But now we have, okay, this is good. Now we have h bar here and h here. H bar is actually just h bar is h over 2 pi. That's right. H bar is h over 2 pi, and it was cubed. But now look at that. That's incredibly convenient that we have an h bar cubed, or h cubed here, and an h cubed here. So this is 1 now. And now we get that this times this equals, and we can move the 2 pi over, so this is equal to 2 pi cubed is equal to delta x delta kx times delta y delta ky times delta z delta kz. So that was the point of the question, is to go from the uncertainty principle of states, which is this statement, just cubing it to get it in 3 dimensions, which is totally fine thing to do. And then they want you to talk about it in terms of the crystal momentum k, which is this k up here, not in terms of the individual momentum P, which is just for like normal states, which is obeys the uncertainty principle. And the relation between them is through this definition, and then you can therefore get that this is actually the volume of the K phase space. This whole thing is the volume of the phase space.
Okay.
This times this, therefore, delta x, delta kx, if this is one-dimensional, is 2 pi. So this is called volume of phase space.
Thank you. I was wondering. Yeah.
Okay, so maybe this clears up the thing I was just asking about, because I was looking at...
You said volume of phase for this one?
volume of the phase space.
And the cube was what again?
The cube is because we did it in 3 dimensions.
No. What was it called? The volume of.
Oh, this is still volume of phase space in 3 dimensions.
phase. Oh, in 3 dimensions.
If we were only doing a one-dimensional crystal, which means that the potential just is, it's not like a 3-dimensional like grid at all spaces, but it's like a one-dimensional thing. It would just be this one. This would be like the length, I guess, of phase space. You could still call it volume though. And that's how we get something that I just wrote, I think. I probably wrote it incorrectly. Anyway, I erased it, but... So this is literally how you do problem 2. Hopefully that kind of makes sense. You might think, why do we need this? And essentially the reason is just to figure out how many electrons we can fit in these things.
In one band?
In one band, right. Because each one can have a value of k, but it's not like you can add... You can say, okay, well, what about k equals 0, and then k equals 0.0001, 0.0002. Like, you can't just, like, always keep... It's not infinitely many.
Okay.
And the reason is because in quantum mechanics, you can't put 2 momenta infinitely close together without messing up their positions.
Okay.
So this is now we're taking a step back and doing a philosophical analysis, which is that in quantum mechanics, it's just true. Sorry, I just want to check if I'm recording. I am. Good. Okay. I got a panic that I forgot to hit record. In quantum mechanics, we can't, given in the same system, this is the same system, we can't have 2 states that have infinitely close momentum together unless their positions are so widely dispersed that they're sort of in different places. That's a not very good way to say it. The point is that because we're trapped in this A region, because everything's periodic, you have to be able to define everything just in this one region with a length A. Therefore, your uncertainty in the position can't be bigger than A, because otherwise you don't know, like, otherwise it's not even periodic anymore.
So this doesn't act like the well when tunneling, right? This is this space that you wrote negative.
No, this is not, okay,
This
right.
is just you're viewing it, you're viewing the band between these 2 points.
Yes, exactly. I'm actually viewing it in K space. These are values of K.
Okay.
These are not values of X. Like if I crossed this out and drew this,
Yep.
these would be this is values of X.
Okay.
But I actually don't really care about X because K is the thing that can change. X is actually like the position.
Right.
K defines the state. So I'm actually each dot. So this is not in space anywhere. This is not a picture of something in space. This is a diagram where I'm able to write in different places the different possible. Each one represents a different wave function. So this one represents if the K value here is K1, this represents psi equals e to the I K1x ux.
Okay.
And if I pick this one, which is all the way at the edge here, K equals pi over a, that represents the wave function psi equals e to the I pi over a x times ux. So we're not free to change, as I said, we're not free to change this, but this K tells you that all the possible states. So that's why we're going so far into, that's why we're talking about K everywhere now. Because K defines the possible states in this periodic thing. It defines the different states, I should say.
Okay.
Because U is sort of fixed by all this. So if we, so that's why, basically, we have a maximum on, so if this is true, so now we're going to 1 dimension. So this is all in 3 dimensions. We're just going to 1 dimension now. We can't have an uncertainty in X bigger than our lattice, because otherwise it's not going to be periodic anymore.
Okay.
So that's not a mathematical statement that I said. You'd have to show something to prove that. But just imagine that if you had a wave function where your uncertainty in its position was so great that it was bigger than the like, if it was like a sine function, it was, if the uncertainty was bigger than that sine function, you'd be like, well, it's not really a sine function anymore, because if I measured it anywhere, I would have I need it to be confined within this A region. If you seem skeptical, I'm with you, because that's a little weak, but that's my understanding. Then, so I'm going up here. If I plug in A here times delta kx equals 2 pi, I get delta kx equals 2 pi over A. This is, I think I wrote this a second ago. I might have written it wrong, but this tells me how much separation do I have to put between my states here. Can I put them infinitely close? No, I can't. I can put them this far away from each other. So it actually depends on A. And remember, A was, again, just the distance between, like, it's the period of the actual lattice in X space, in real space. And K space here is now just one region where I talk about, okay, K is also periodic because this is a plane wave which is periodic. So K can only be between negative pi over A and pi over A, which is why I wrote it like this. But this is the number of sites I have. And then in the book, right before question 3, I believe, they write the total number of electrons in a band. They ask you something about it, but then right before that there's a thing that says NL equals, I think it's this.
NL electrons unit per unit length. You get a picture.
I think it looks like this.
Yeah. Yeah.
Okay. So this is the number of electrons that can fit in this band.
Got it.
So you can kind of see where it comes from. The 2 here is just because there's 2 per state. So this should be the number of states. And kf over 2 pi is, what's kf over 2 pi? That is the length. Oh, that's, sorry. Why am I, okay, I'm getting confused again. Somehow we should be basically saying the total length of this is 2 pi over A. The total length of this region is 2 pi over A, and each state takes up this much space. So if I divide them, hopefully I get this.
Say that again?
So if all I'm doing is trying to count how many dots I can put.
Yes.
If the total region is 2 pi,
Yep.
and that's what it says somewhere in the book, but in his notes it says length.
Each dot representing one spin up and one spin down electron in the length
of K space 2 pi. That's this whole thing. This is 2 pi.
Oh, from negative. Yeah. Okay, that makes sense.
From negative.
Thank you. Yep.
You could put 0 to 2 pi if you'd like.
Yeah.
But, I'm barely holding on. So,
Yep.
But this is 2 pi. So then, if you say how many slots can you fit, if the separation between each slot is this,
Yep.
2 pi divided by this actually is not this.
2
Okay.
pi divided by.
Sorry, I thought for some reason
You're looking for delta K.
it should be 2 pi divided by
Delta KX.
By
No,
delta
sorry,
KX.
delta X. Delta KX equals 2 pi divided by delta X. That's what it says here.
delta kx equals 2 pi divided by, yeah, that's true.
Which that makes sense. Okay.
Yeah, so that's this.
Why did you swap out for A?
Oh, because that was the maximum. That's defined, so that's in general true, but we know the value of, if we want to pack them close,
Yep.
we know the maximum value of delta x is A.
Oh, okay.
So I just plugged in that here.
So what you wrote is, it's the change.
What I wrote is the distance, this is the length that each state sort of takes up.
Yep.
The width, I should say, that each state takes up.
Okay.
So what I'm trying to do is say, I think it's just 2 pi divided by the length of each state should give you the number of states, but it's, for some reason that's not. Sorry. Okay, I'm making a. Okay, I meant to do something else before this.
Delta kx is the length between the states.
Yes,
Okay,
delta
okay,
kx is
okay.
the length in this diagram in the Brillouin zone, which is just means the E versus K diagram. Because remember, the states are I'm listing all the states because I'm changing K. So if I put all the dots in there for each value of K, then how closely can I pack them? The only reason I can't pack them all infinitely close together is because of the uncertainty principle. Because if I pack them infinitely close together, my delta x, my uncertainty in their position, that means that I know their momentum very precisely. And if I know their momentum very precisely by the uncertainty principle, I know their position very imprecisely, and then I can't keep this periodic condition anymore. It could be sort of all over the place. I don't know that it's periodic anymore. That's sort of a rough way to understand it.
Okay.
Of course, there's all this has mathematics behind it that I'm not going into.
Okay.
That I don't actually think is worth any person's time.
Thank you.
Which is probably not a very polite thing to say to people that actually research this, because people spend their entire lives doing this.
I don't think anybody here is going to be.
Okay.
I really.
But anyway. But anyway, so as I was saying, we know because of the so this is I should just really write uncertainty principle, because this is like a new quantum thing that we haven't talked about yet, right?
Did he go over that in 11? He had to do it.
It was probably in 9 briefly.
Yeah.
But we didn't do anything with it yet. This is the first time we're really doing something with it. Also, these are electrons. Just keep that in mind. These are all electrons. If these were not fermions, remember the Pauli exclusion principle says that you can only fit. That's again, I erase everything that I need. Oh, each state has 2 electrons.
Okay. Yep.
Why can't you just put pick this state, the bottom one, and just put 1,000 particles in it? Why can't you just do that? Well, that's because each state each fermion has to have a different set of quantum numbers. So therefore, because electrons can have a spin up and spin down in every given state, you can't have 2 spin up in the same state because then they have exactly the same state, including spin.
Oh, you couldn't identify the difference?
Exactly. That's a rule about fermions.
Okay.
Which an electron is an example. So fermions cannot have the same state, and the state includes not just this but also their spin. So when I shouldn't really say state here, but you know what I mean, like energy state.
Yeah. No. I think we.
But if it was there's other particles called bosons, and like photons are examples of the. If I was talking about photons, there's a whole issue with they go at the speed of light, but pretend that doesn't exist. You could fit infinitely many in any state. So we wouldn't have any of this issue. No one cares about this. There could be any uncertainty. We could just shove them all in one state.
Because photons.
Exactly, they're not fermions. They're a different type of particle. So the Pauli exclusion principle, which gives you this, Pauli exclusion, gives you this. The 2 doesn't come from Pauli exclusion. The 2 comes from the fact that electrons have spin 1/2.
Got it.
Therefore, there's an up and down. If we could, there's other particles that are fermions that have spin, that have spin 3/2. Okay, there aren't actually in real life, but there could be.
Okay.
Don't worry about the fact that there really aren't. If there were, then we'd have a different thing to consider here. But anyway, so so I'm just trying to point out. So I'll actually put it in red. Everything I put in red is a quantum mechanical feature that we consider now, which is this case. There's 2. Of course, the whole wave function is quantum mechanical, obviously, but it essentially comes down to solving the Schrodinger equation, which is just a regular equation. There's nothing super special about it. These 2 are new quantum mechanical things that restrict us to, why we can put the dots and where we can put the dots and all that stuff. What was I going to do? Oh, okay, then I was going to talk about the Fermi energy. Okay, so I'll draw that again. So this is 0, then I'll draw the separation is still delta K.
Yep.
And this is all one-dimensional still. This was 3, so I'll erase all the 3-dimensional stuff because that was problem 2 asked you about 3 dimensions, which is this, but all the other problems I don't believe you need them. I'll even erase this for now because we don't need it anymore. I guess I'll leave this. Okay, so now I'll erase this. Now let's say you have a bunch of electrons in some band, and they ask you what the Fermi energy of the system is. Now, what that means is that, remember before when I said I have 12 electrons, how do I fill them in the infinite square well? So remember, I stacked them, and I just started with the lowest. I put it up and down, and the next one I put it up and down, and I filled them up, and then I got to some, basically, it's like filling up a pool. I put my electrons in the lowest states and filled them up like a pool, and then said, what's the level of the pool? So if I have that same thing here, what if, let's say I had, however many this is, electrons. Each state, so this is up, down, up, down, up, down. Let's say I had, 15, or sorry, not 15, however many this is, 2, 4, 6, 8, 10, 12, 14, 16, 18. Let's say I had 18, hopefully I counted right. Whatever, 18 electrons, okay? If then they said, what's the Fermi energy of my system with 18 electrons? What I would do is just draw them in the lowest states, right, until I get to here. So now I'm done filling them up. This level here this is an energy level, and this is called the Fermi energy.
No, I'm staying here tonight.
Fermi energy.
I was telling you last night,
So what it means is that if you were to hypothetically, with zero temperature, and the reason you have to say zero temperature is because any temperature is actually excitations of molecules, and so with some temperature you can have random jumping. But pretend everything's just settled all the way at the bottom, pack them in as tight as you can. How much energy you get up to? That's called the Fermi energy.
Right. Okay.
So that's what the Fermi energy is. The other example, it's also in with the square well.
Yeah.
It's still the Fermi energy. It's fine. It's just that generally they talk about it with these systems.
Define a little bit.
And so now this depends on, obviously depends on a bunch of stuff like A and how big this is and what the bands look like. Because of course, well, it doesn't depend on what the bands look like, but it does, because let's say you had a bunch of electrons and they filled this up, then you would need to go up to this band. You couldn't put any electrons in here. So let me draw this a little better. Let's say you had this. This is a band. This is another band. Let's say they say you have this many electrons. And so there's a bunch of dots. And let's say you fill this up and you have more electrons that you want to put in. You can't just put one in right above, like there's no states here. The next one would have to be here. And then maybe here, and then maybe here.
So that gap is even larger.
Yes, exactly. So this now would be your Fermi energy.
Oh, I meant the spacing between the electrons.
I mean this. So in other words, you'd have electrons. If you listed the energies of them, you'd have 0 and some number. You'd have some number here, and then you would jump right to this number. You'd have no electrons energies in between here.
Okay.
So something is called a metal or a conductor. If you have very few, hold on, let me make sure I'm saying this right. If you have like a gap, if you have a band that's partially full. So if you have a band that's partially full, that means that your electrons can kind of flow in this band very easily. It doesn't need to overcome anything.
Okay.
So if the Fermi energy goes through a band, could be the lowest one or not the lowest one, doesn't matter. This is a conductor or a metal. There's a definition of metal.
If your electrons flow through a band?
No. If the Fermi energy goes through a band.
Oh.
Because what this means is that your electrons here can just like they can just operate. They don't need to overcome any energy. So that's the key point of a conductor. Is that to excite this electron, you can just give it like a very tiny amount of energy. You can just jump right up to here, right? So this is a conductor.
So yeah, if your Fermi energy goes through a band, you have a conductor?
Yes.
Okay, that's what you said, yes.
Yes, and if you have, so this would be a conductor. Let's say you had the same state like this, but let's say your Fermi energy was here. I mean, it couldn't be here, I guess. It would be like here. So let's say this was all filled up.
Mm-hmm.
so therefore your Fermi energy was here, but you didn't have any more electrons up here. Now, to get if this is your material,
Yeah.
that means to get an electron to start like flowing around, it would have to jump up all up to here because this is the next state. It would have to overcome this gap.
Wait, so that one's not being considered going through a band?
Sorry, say it again.
It's not. You're not considering that one going through a band.
This is a band and this is a band. This is a gap.
Right. So, but you said the top one. You had a
Charlie,
band.
There's a young lady.
You had a band going through
Yes, this is a band.
a. I'm sorry.
The Fermi energy lies inside of a band.
Okay, you're saying here the Fermi energy does not
Do
lie.
you know who
over
she
there.
is? Take a
Sorry.
look when you feel like it. Yeah.
Okay, what I'm trying to say is that if you wanted to move this electron around,
Yeah.
you would just need to give it a tiny amount of energy, and it would just be still in the band. And now it could just do whatever it wants. It could
Oh,
it could get
okay.
out of the pool very
Okay.
easily.
So like
This one
that
to get out of the pool would have to jump over a big thing.
but it can go down. No.
Yeah, they can rearrange and
That's
stuff.
okay.
That's
So
fine.
that didn't change.
Yeah, sorry.
I
You're-
thought you were saying.
No, you're
We
right.
just-
How
okay.
I said it was not
Thank
correct
you.
because
Yep,
it does
okay.
kind of go. I really should write the Fermi energy as like slightly above this band.
That's how you described it before, and I was like, wait a minute.
Yeah, I should write it as like above here. I just didn't quite want to say it because Fermi energy is supposed to be the energy of the highest excited electron.
Right.
So technically it should be right at the top. But the point is that to excite an electron to get it to move through the material, I have to get it to jump all
Yeah.
the way up here. I have to get it to overcome a gap. That's hard. So this is an insulator.
So for the top one, I was confused because if it flows down or if it flows upward, like from our view, it's going down in energy states, right?
No, it would have to have more energy to go up here, but not that much more.
But is it considered below the Fermi energy? It,
Oh,
it
it-
can't go above it.
Yes, it can. No, it can.
Oh.
Sorry. Okay. Let me
Okay.
say this again. I understand your confusion now.
Okay.
The Fermi energy is just if all the electrons were in their lowest possible states,
Okay.
what would be the height of the pool?
Okay.
But every things like electrons flowing through metals happens when they get out of the Fermi. Like that's the height of the pool if it was at rest. But when you get in the pool, this is a silly analogy, but you get splashes.
Yeah.
And splashes if something splashes, it can just go right up here, and that takes very little energy for it to flow to do whatever it wants now. It can just easily get to the next energy.
Okay.
This, if you wanted to make a splash, this is why it's a bad analogy, but to get anything excited, you'd have to give it a bunch of energy to get all the way to the next band.
Couldn't give it enough.
Right, you could.
Oh.
It's possible, but it's very difficult because it has to overcome a gap. Here, there's no gap.
Okay.
So essentially what it means is if you wanted to excite an electron, do you have to overcome a gap or not? If you don't have to overcome a gap, it's a conductor because it's very easy to do that.
Okay.
So it conducts. I'm mixing my metaphors, I guess, but therefore it's very easy to transmit electrons. So if it's a metal, let's say you're saying you want to push a bunch of electrons, it doesn't do it by itself, so it's not automatic. But how much energy you need? This much, which is like nothing. Especially because these states are like super, 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 super close together. So how much energy do you need? Very little to start exciting an electron. Here, how much do you need to start exciting an electron? A whole bunch, because it has to overcome this giant gap.
Got it.
So you could still do it, it would just be much more difficult. And so this is an insulator. And this is a conductor. And it just depends on where the Fermi energy is. So it literally depends on what the bands look like and then how many electrons are in there. Because of course, if we just drained the electrons out of this, it would look, and so then the Fermi energy would go down, it would look like a conductor again because then the Fermi energy would go right through a band and you could just easily excite the electrons.
When you have that gap, I assume the opposite. You have an insulator.
Exactly.
Got it.
And then a semiconductor.
Oh, you wrote that. I didn't even pay attention.
So a semiconductor is not quite something completely different. It's just an insulator, but if this gap was very, very small. So imagine an insulator.
Yep.
But let's say the band gaps were like this. So this is the gap. And here's your, sorry. I'm just trying to draw these dots again. You have a bunch of these. Now your Fermi energy is here, but it's not like this one where an insulator, you have to overcome a ton of energy. If your gap is very, very small, and you can make materials like silicon, just happens to have bands. If you look up a silicon, I don't know, whatever, you'd have to look up some stupid chemistry thing. You'd find that the gap between its two bands is very small, and so it takes a little bit of energy to overcome, but not like a crazy amount. So this is a semiconductor. Exactly, because it can be easily turned into an insulator by just, like, in other words, this, if you give it like just the smallest amount of energy, it will move electrons around.
It can act as either, depending on how much.
Exactly. This, if you have to, it will do nothing unless you give it a ton of energy.
Yeah.
And this has a medium amount of energy, and that's perfect because electronics want to sometimes conduct and sometimes not.
Right.
So how do you do that? Well, you just have to control. If you use this as your semiconductor, you would have to have such high control of the energy. You can't have any, even like temperature fluctuations would bounce these around.
Yep.
You want it to be big enough, but not so big that now you need like a battery top, like a giant battery to operate like a power plant. If you tried to make a computer with chips made out of, whatever an insulator is, plastic or something, you could do it. You could actually do it. It would just be really difficult because every time you excite it, it wants to fall back down. So somehow you got to keep it going. This is perfect because it can very easily be a metal. Specifically, maybe if you heat it up. If you heat it up, you can actually change the band structure so that they get a little closer together.
Okay.
And then it becomes more of a conductor. And if you cool it down, it gets farther apart, and then it becomes more of an insulator. So that's the three types. It all has to do with how these electron states. What's their next? What do they want to do?
Yeah.
If you give them, if you want to move them around, what do you need to do? If it's hard, sometimes you want it to be hard, sometimes you want it to be easy, and sometimes you want it to be kind of hard and kind of easy.
You want to be able to control that. Though,
Exactly.
which is what you give it.
Yeah, and then did he talk about the types of semiconductors?
Refresh my memory. What are they?
Like hold on. There's an N type and P type.
Maybe.
So the thing is, I'm not gonna. Nothing about this was in the homework, so I'm not gonna get into it.
Okay.
Also, I remember like enough to talk about it for maybe 10 seconds. It's something to do with N type contributes electrons
Got it.
in this way. Oh, actually, I can talk about it for a second. I'll just say it. It's not on any of the homeworks yet, so I doubt it'll be on any of the homeworks. But if you want to know.
Guys, pizza?
Absolutely.
Oh,
Yeah.
thank you.
Thank you.
And if there's any left, Ryan's all over.
Oh, sure. So remember how I was drawing these dots here? You can actually do this entire, well, I don't know how to draw it in this picture. The point is, if you can contribute an electron to this layer so that it flows around, this is called an N type. So contribute means contribute means make it into like a flowing one, a conduction one.
Okay.
So in this case, I should say this is called the conduction band. In this case, this is called the one where the highest electron is called the valence band.
Okay.
Right, because the valence electrons are the outermost ones, right? So if the valence band is very far away from the conduction band, that's here. This is the valence band because that's where all the electrons are in the thing. This is the conduction band because that would be where conduction happens. Conduction band is just like the highest one, basically.
Okay.
Anyway, sorry. I just realized that was in his notes. But an N type means that electrons have to jump in a semiconductor. So if electrons jump, they're called N type. Now this is where there's an entire field that I couldn't go into, but one could go into. You can talk about electrons moving around, but you can also talk about holes moving around. HOLES. There's an entire description of electronics where you don't talk about electrons moving, you talk about places where there's no electrons. So here, an example is that, and I won't go into this too much because
Are you observing that
It-
one's left?
Huh?
Are you observing that one left?
yes.
Okay.
So it's basically like how hydrogen, let's take like magnesium, has a bunch of, or whatever magnesium is. It has like two valence electrons.
Okay.
So it has a bunch of electrons in here that don't do anything, but then there's two that can go about and conduct things and can flow. That's with the metal.
Sure.
But you could also have something like, this is probably not a very good description if like someone professional heard me, like a person that researches semiconductors heard me, they would probably be really disappointed. But if you have something like maybe chlorine,
Okay.
I'm not positive this is how it is, but chlorine has 7 valence electrons, and so it has one sort of missing. That's why it binds with metals easily, because metals have extras, like sodium chloride,
Yes.
right?
Yeah.
It actually is a hole, but you could actually talk about like if another electron filled in this hole, then there would be a hole here. So instead of talking about electrons moving, you could actually say that the hole moved this way, and if that's what's happening here, if you could talk about it as a hole goes to here, and that means that really an electron went up here, but somehow there's a little picture of an actual molecule that does this. This is not really correct, but there's pictures in the last two slides. That's called a p-type. P means positive and N means negative, by the way.
Okay.
Negative because the electrons are negative and then they're moving. With a p-type, holes are places where there's no electrons, so it would be a positive ion. Yeah. So you're saying that the electronics happens in the positive ion parts, which is places where it's missing an electron. Now you might think, aren't those like the same thing? And I would say, yeah, I think so. So I don't really know. But that's all that's in here, and I'm sure there's more in. First of all, I'm sure there's more on the internet, but there's probably more in the book if you want to learn more. I won't go into it anymore because again, it's not on any of the homework. So, but also on the homeworks. I talked about 1 and 2.
Yep.
Number 3, I'll get to in 1 second.
I thought you did talk about that.
Oh, number 3 involves salt plugging into this,
Yeah, I had that written down.
and I believe number 3 involves solving for this. I'll write one more thing that you might need, which is that the Fermi energy is equal to h bar. Hold on. Yes, h bar times the Fermi momentum. So this is kf here, Fermi momentum.
Yep.
Sorry, I should, I didn't tell you what the Fermi momentum is, I forgot. So pretend this is my band again. It looks like this,
Yep.
and here's my states. Let's say this is my states, so therefore this is my Fermi energy, right here. This value, and if this is 0, then it's this distance here is the Fermi momentum. So
Okay.
all it is just the momentum, meaning the k value of the highest state. So it depends on the band and all that stuff. Actually, okay, that looks a little strange. Actually, that might not be true, that picture. This is true. Can't be true because it's not linear. But anyway, the point is that this is true, and so you might need this, I think, for this question. I'm not positive. But anyway, so 10.3, just,
11. 11.
sorry, yeah, you're right. 11.3,
No.
I believe involves this, and maybe this, and this is one of the ones that, to be completely honest, I'm not positive what the answer is.
Okay.
I'm positive up to a factor of 2 and a factor of a. So as usual, with all the homeworks, do your best, but you don't even have to do your best. You can just, don't worry too much about 11.3. Then there's the 4 questions from the end of the book.
Yep.
I'll write some equations those are a much, I don't want to say much easier, but they're a lot less convoluted than the first 3. And I'll write some equations that I think you'll need for each one. There'll be like hints. But as usual, I don't want to just like sort of tell you the answers, even though I kind of have already.
Yeah.
But I'll write these, and of course you can Google them and find things. But for number 2, remember the equations. Here, I'll write them on the board. P equals h bar k, which equals h bar times 2 pi over lambda. This is the definition of k from p. So momentum p is, in terms of the crystal momentum, it's called k. And then k is just 2 pi over lambda. So you might need this. And I think you have to plug something in from that. I don't remember. I wrote some just hints to tell you. This one is this. This is the photon energy in terms of its momentum. That's all I wrote for this, so hopefully you can figure that out. This one is also about photons. It's, remember this thing. Okay, these are all true for photons. Everything about E here is true for photons. The energy of a photon is given in terms of wavelength like this. You could also write it as h bar 2 pi c over lambda, which is the same as this. You could also write everything here as omega, the angular frequency. I don't think you need these ones, but they appear in, I believe they show up in the book or something. That's why I wrote them. Anyway, I think this is the only one you'll need. And when they say longest wavelength, so they ask you something about what's the longest wavelength. Longest wavelength means the biggest value of here, right? And these are constants. So that means the smallest energy. So remember when we did photons before, it was kind of confusing because sometimes they would ask you about the smallest wavelength, which is actually the highest energy. It's a little weird. You just have to remember this equation here.
That's actually.
So smallest.
I was gonna say that's a basis for my entire industry. But
Oh, well, there you go.
There you go.
And also, so keep in mind that remember when we're talking about. So in class, obviously the sort of one of the main things we've been talking about the last few classes are if you have all the states of a quantum system, electrons or anything can jump between any 2 states.
Okay.
So remember with the cube, I keep going back to the cube one, but we had like a 9 and like a 6 and a 3 or whatever. That means that if you go from like the 6 to a 3, you get 3 h bar squared pi squared blah, 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 amount of energy. So you can have a photon or a 9 minus 3, which is 6 amount of energy. So you can go from any state to any other state, and it radiates a photon with the energy equal to just the energy, the gap in the energy, because energy is conserved, of course. So in this case, they're asking about the bands, and going between the bands is the same exact thing. It just costs energy. Instead of having like 3 states, we have like a ton, because like we have a bunch, right? But going between here and here still costs this much energy, gap, right? So when they say, they ask something about, I forgot what it is, it's like they ask you about a bunch of materials and say what gives you the longest wavelength photon from going across the band gap or something. And all you have to do is think about, well, if I want the longest wavelength, I want the smallest energy. And if I want the smallest energy in this transmission across the gap, I need the smallest band gap. And they give you, I think, a list, and I believe you're just supposed to look them up. Sorry, you're definitely supposed to look them up because I don't know how else you now know them. So this you can look up.
Oh yeah.
There should be a table or something somewhere. And number 6, I don't know. It asks you about it asks you about things that I know about very well, but it asks you in a way that is not correct. I don't want to say it's not correct. It's not. They clearly want to give you a simplified version of what they're talking about in such a way that I don't think it makes any sense. What they're asking about is something called the density of states. So you can kind of think of that as like how many states are there and what's the length, right? But they ask you about it in real spatial dimensions, which is sort of not really that's not really how you're supposed to talk about it. So I'm not totally sure. They ask you something about the Fermi energy. Just write something for here. Try. Write something really genuine. Like I know I'm saying this, and now that means that no one's going to do it at all. But really do really do try to answer the question. If you maybe I'm just reading it completely in a stupid way, and someone will see it and be like, no, it's just because it can't be that hard. Like these are relatively simple equations. It can't be like that complicated. But to me, it sounds like something that would take several integrals. What they're saying about the density of states is defined by a bunch of integrals that I know how to do. I would not like to do them anymore, and there's no way they're asking you to do them. So anyway, that's why I'm a little confused. So I'm just going to say try it. If I couldn't figure it out from reading it a few times, you don't have to, I'm not going to hold you to that standard, but really try to do it because, I mean, it may show up on the quiz. I don't know.
Yeah.
I doubt it, but.
Well.
But anyways, these are hints for, this is at the end of the chapter.
Yep.
And as I said, 11, the within chapter questions 1 and 2 I've basically done in this video. And 11.3 I said some stuff about, and hopefully you can put it together.
Okay.
It also seems like the same, 11.3 seems very similar in, not this one, but in chapter 11.3 seems very similar in that I don't quite know what they're trying to ask, but all the pieces on the board are basically where I'm at. So if you can put it together and give an answer, it's probably going to be right. And that's the homework.
Yep. Okay.
And hopefully the homework will not impede you from understanding this, because it sort of did for me by looking at it. The homework seems kind of disconnected from it. I don't know. I'm hoping that he's just trying to get you to think about these things. Like, this is a very cool, interesting concept that tells you really what do you mean by an insulator or conductor.
Yeah.
It's these things. There's really a physical system, and then they ask you to compute, like, E equals PC and stuff. So I don't quite get the relation, but hopefully I think I've done everything on the slides, which I think is the part he wants you to really, have an understanding for. And the big takeaway of like the big new thing is that filling up the states is not so easy anymore. It's not just like we get some quantum numbers, we get n, x, n, y, and z, and you just pick some numbers. And it's not like we get n and l and m like in an atom. We get a quantum number k because it goes in e to the I kx u of x. So we get this quantum number k, but k is not necessarily an integer like the other ones. The other ones we had to have integers because of boundary conditions and all that stuff. But this is not an integer. This is a real number. But we know we can't have stacked, they can't be any real numbers because we know we have to have this separation, delta k, which is given by the uncertainty principle. Okay. So that's how it's still quantum mechanics. Because it sounds like if we have a quantum number that can be any number that's not an integer, it sounds like then you're not doing quantum mechanics anymore. You're just doing like, classical mechanics. In classical mechanics, you can just, there's nothing like this. But it is quantized because there is a finite separation that you have to have between each thing. And that comes, in this case, it comes from the uncertainty principle. It does not come from boundary conditions like it did last with the wells and stuff.
Okay.
It's a little different, but it's from, basically if you do question 2, the one from the chapter,
Yep.
Within the chapter 11.2, that's essentially the statement of telling you why it's quantized, why you can only fit a finite number of electrons here and not just pool them all as close together as they can.
Got it. Okay.
Because of phase space is if you had to say it in 2 words, you'd say it's because of phase space. But hopefully that makes sense after you do the problems. And also I would genuinely, I know I say this a lot, but like genuinely read the chapter in 11 because it's not super up to question 11.3.
Yeah.
Because after that, I don't think you really need it, but read it up there because it's actually not very long and it's essentially like just what you need to do the questions and stuff.
Good.
So I would really try to read that because you're not going to get a bunch of stuff you don't need, and if you search online, you'll get way too complicated stuff. You could search Bloch's theorem online, it'll give you a proof and it'll give you a bunch of nonsense you don't need. Or you could, I think, should read in the book up to that second because, again, it's only a few pages and it's much better anyway. And hopefully with these hints, you can do the homework with not too much trouble. And then as we get closer to the quiz, I'll figure out what he's going to actually ask you as opposed to like, I don't think it's going to be a mixture of these homework things. I think it's going to be a little more like qualitative, like these. So then we'll focus more on those things.
Yeah, so like I said, the concepts.
Yeah.
I'd like to understand that, but
Yeah.
the math I get hung up on.
Right.
Could you go over the